In this video, we're going to return to some topics that we've talked about previously, but apply them to power functions. So it's a little bit of review, but also now that we've been able to look at all these different characteristics of power functions, we can really see how these apply. So this first one, we're just going to talk about some graph behavior. So what we have here is this looks like a cubic function or an odd powered function. It's maybe been reflected. But let's just kind of talk through what we're seeing here. So in terms of increasing, decreasing, we're decreasing, and then we're going to keep on decreasing. So this one doesn't change behavior anywhere. So if I needed an interval for increasing, well, there isn't one. So there's no increasing. And then decreasing is occurring from negative infinity to positive infinity. Okay, let's see, relative extrema. We actually don't have any here. Now, if this graph had some bumps to it, like this, then we would have some local minimums and local maximums. But this one flattens out right here. And at that point, we're not creating a peak or a valley, so there are no relative extrema for this graph. So far not terribly exciting, but just to apply that terminology to this graph here. Now, long run behavior. So if we're asked to define long run behavior, I want to describe two things. I want to describe what f of x approaches as x goes to the right. So as x goes to positive infinity, f of x is going towards, it's approaching. So as I'm going off to the right, my graph is going down, which means we'd be approaching negative infinity in the long run on the right-hand side. And then on the left-hand side, I would say as x approaches negative infinity, f of x is approaching. And what I could see is on the left-hand side, so as x goes to negative infinity, my graph is going up. So that means our function is approaching positive infinity. So that would be my long run behavior for this graph, be kind of fitting in those sentences. And just to give you an idea, I know we talked about this a bit before, but this is the sentence structure. And really what I'm fitting in, or filling in rather, is whether we have positive or negative infinity there. We'll see some values with rational functions later on. But for now, we're kind of filling in infinity with these. Okay, let's talk about concavity. So over here, I have something that's roughly shaped concave up, and then over here, shaped concave down. So what that means is there's a point where it switches, which is going to be right here at that flat spot. So that means I do have an inflection point. Even though they didn't ask for this, let's go ahead and answer. We have an inflection point at -1, -3. And what we have is to the left-hand side is concave up. So our interval for concave up would be from negative infinity until we reach that x value of -1. And then it switches to concave down, which begins at -1 and goes off to positive infinity. So that's how we could describe some pieces of a graph of a power function. Okay, now what we're going to do is we'll be given two power functions. We have 2x to the fifth and -3x squared. And let's take a look at composite functions, inverse, average rate of change, and difference quotient with these. Okay, so composite function. We want f of g of x. So what that means is I want to take f of, and g of x is the -3x squared. So f of x tells me to take 2 times our input to the 5th power, and our input is going to be that -3x squared. Okay. And now I'm going to simplify. So let's actually move over here. And for now, I'm going to keep that 2 out front. So what I'm going to do is think of this as -3 to the 5th power and x squared to the 5th power. Now, 3 to the 5th power is equivalent to 243. So let's keep the 2 there. And then because it's negative raised to an odd power, that's going to stay negative. So negative 243. And then here we have our exponent property, power to a power, so we multiply those together. So that'll be x to the 10th power. And one more step here, 2 times a negative 243 is 486. So I'm going to have negative 486 x to the 10th. And with that, we actually end up with another power function when we create a composite function. And then we're done. So next up is an inverse function. And something I want you to notice is in terms of taking an inverse, so we're going to take the inverse of f of x. But what if I had asked for g of x? So something we want to notice is with that even power, that's where we're graphing something like a parabola, which is not one-to-one. So if I wanted the inverse, I would need to do some restricting of the domains, like say only looking at this part of the graph, because we need to pass that horizontal line test to take the inverse. However, with odd power functions, we'll be okay, because odd functions are one-to-one. No matter where I draw that horizontal line, we will pass that horizontal line test. So we'll not be taking the inverse of g of x. So we'll talk about that in a later video when we're talking about our quadratic functions. But for now, let's take that odd function, which is y equals 2x to the 5th. And to find the inverse, what we could do is switch our x and y values and solve for y. So first up, I'm going to divide by 2. So I would have x over 2 is equal to y to the 5th. And now next up is a piece that maybe you haven't learned about before. So maybe this is new. We'll be practicing this more when we get to our radical functions in the following weeks. But just to take you through the steps here, to get rid of that exponent of 5, what we use is, like say we were trying to get rid of an exponent of 2, we take a square root to cancel those out. So if we had something to the 3rd power, we would take a cube root. So if I have y to the 5th, what I want to do is to take the 5th root of both sides of the equation. Now, when we take the square root of both sides, remember that brings through the plus or minus, and that's only true with the even roots. When we have those even roots, we'll have the plus or minus. When it's odd, we do not have the plus or minus, because we can take the cube root of negative numbers, and it will give us a negative value out. Okay, so all of that to say, we need to take the 5th root of both sides so that there's this nice cancellation between the root and the exponent. So that means y is equal to the 5th root of x over 2. And that would be our inverse function. And to really finish it, let's go ahead and bring in that inverse notation for that 5th root of x over 2. Okay, let's apply an average rate of change to f of x. So again, f of x was, or rather is, the 2x to the 5th. And what we're going to do is take f of 2 minus f of negative 3 all over 2 minus a negative 3. So let's go ahead and find these. So f of 2 is the equivalent of 2 times 2 to the 5th. So using a calculator to help us out, so 2 to the 5th is 32. Multiply that by 2 is going to be 64. And then if we plug in a negative 3, so negative 3 to the 5th, that's going to be that 243. So this will be the same as 2 times negative 243, which was the 486. So negative 486. Okay, so f of 2 is equal to 64, and then we're going to subtract a negative 486 all over a 2 plus 3, which is 5. And let's go ahead and simplify that down. So 64 plus 486 is a 550, divide that by 5. So we're going to have an average rate of change of 110. All right, so same routine as previously. This is just to show it with a power function. Let's go to the difference quotient here. We're going to use g of x for this. I'll tell you why we did not use f of x, but let's go through with g of x here. So g of x is equal to negative 3x squared. And then we want to also look at g of x plus h. So that would be a negative 3 times x plus h squared, which is the same as a negative 3 times x squared plus 2xh plus h squared by FOILing that out. And then distributing the negative 3x squared minus 6xh minus 3h squared. So let's go ahead and plug in. So this negative 3x squared minus 6xh minus 3h squared, that's all going to replace g of x plus h. So let's plug that in. And we're going to subtract negative 3x squared. So that's really going to turn into a plus 3x squared, all divided by h. And our goal with this process is to cancel out that h in the denominator. The idea being eventually, and this is more of a calculus piece, is that we would be plugging in h, or we plug in 0 for h. So we don't want that denominator to turn into a 0. Okay, so with that, we're going to see negative 3x squared and plus 3x squared. That's going to turn into a 0. And then what I'm going to do is I'm going to go ahead and take a common factor out. I have a common factor of negative 3h in that numerator. So that'll be a positive 2x plus h all over h. And now we can cancel those h's out because we factored it out. So it can divide away. So we're left with a negative 3 times 2x plus h. And you can leave it like that, or you could distribute it back in, negative 6x minus 3h. Both of those would be good answers there. Okay, let's talk real quickly about why I did not do a difference quotient with the 2x to the 5th. So, and we could, it's very possible, but what we would need, so f of x is 2x to the 5th, and what I would also need is f of x plus h, and I would need to simplify it. So that would be 2 times x plus h to the 5th. And to expand that out, what I would need to do is think of it as this. Which we can absolutely do. What we could do is FOIL this, wait for that last one, and we would have these expanded, x squared plus 2xh plus h squared times x squared plus 2xh plus h squared times x plus h. And then what we could do is our multiplication of polynomials here. Oh my goodness, there'd be so many pieces. There. And then once you got that monstrous polynomial, then we would multiply by x plus h and multiply that on through to absolutely everything in there. So if you want to try it out, go for it. But we're going to pretty much stick to squares. We could go as far as cubes, wouldn't be too bad here. But that's kind of why we didn't do a difference quotient with that one, is it would just take a lot of work to expand that x plus h being plugged in. All right, so there's some properties of our power function.